Now, the reactions of haloalkanes. So the first reaction, we can say different types of reactions are there for haloalkanes. The first one we can say nucleophilic substitution. The other reactions are elimination reaction is there and reaction with the metals. So first one is nucleophilic substitution reaction. So nucleophilic substitution means when a nucleophile is coming to the compound, that nucleophile can remove the halogen atom and they will take the position of the halogen atom. So the nucleophile is substituting the halogen from the alkyl halide. That is called nucleophilic substitution reaction. Okay, suppose I am taking the alkyl halide Rx. Okay, suppose one example I am taking CH3X. Either means here we can say other than the compound here, other than this compound we can take a chloroethane, bromoethane, any compound. So I am explaining this example using one specific thing that is chloromethane. So I am replacing this halogen with chlorine. So I'm writing chlorine here. So CH3Cl, right? So C, hydrogen, 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 chlorine. So here, this chlorine to be substituted by the nucleophile, that is OH minus or any other nucleophile. So that is called nucleophilic substitution reaction. As I said before, normally the carbon halogen bond have a partial polar character. Because of these electronegativity of the halogen atom, the chlorine atom have more electronegative and carbon is comparatively electropositive. So due to the high electronegativity of chlorine, they are dragging the electron density from this carbon. So chlorine atom is getting a partial negative charge and carbon atom is getting a partial positive charge. Means this bond is polar in nature, right? So when the halogen is coming, halogen means when the nucleophile is coming, nucleophile means they likes nucleus. They likes nucleus means they have a negative charge, so they likes to bind with the positively charged nucleus. So in case of the nucleophile, normally we can say due to the electronegative nature of the chlorine, due to the polar nature of CCl bond, the OH minus is replacing chlorine from the haloalkane and the alcohol will form. If it is the nucleophile is OH minus, the alcohol will form. Okay, see, here the halogen is called the leaving group and OH minus is the attacking group. Okay, see here, this is the nucleophile. So this is the alkyl halide, X is replaced by R. Okay, so now this is substitution reaction, but the substitution reaction can be done by two mechanism, SN1 mechanism or SN2 mechanism. That is the important thing regarding this one. So before that, we are explaining one more thing, that is ambident nucleophiles. Ambident nucleophile means, see, here if you take the nucleophile CN, here this group can, see, example, the cyanides and nitrate groups possess two nucleophilic center, means they can bind to the metal atom either through carbon or through nitrogen. At the same time, they cannot use both the donor atoms. Okay. At a particular time, either they can use carbon or they can use nitrogen. So that is called, that type of ligands are called, or nucleophiles are called ambident nucleophile. Okay. So now we are moving to the substitution. So substitution reaction means we are substituting the halogen atom by using a nucleophile. That's why they are called a nucleophilic substitution reaction. So in nucleophilic substitution reaction, we have two mechanisms, that is SN1 and SN2 mechanism. So in SN1 mechanism, we have different method. SN2 we have different method. First, we are going to explain SN2 mechanism. SN2 mechanism, we can say it is a single step process. It is a one step process. So in SN2 reaction, we can see the same. One more thing is there. In SN2, the product is having the configuration that is opposite to that of the reactant. See, this is the compound. I am taking bromomethane. So here OH minus is attacking. So here the bond breaking in SN2 mechanism, S denotes the substitution, N denotes nucleophilic, 2 denotes bimolecular. What is this bimolecular? Okay, we will discuss about that. Before that, here when the halogen is, see here this bromine to be replaced by the nucleophile OH group. So when the OH group is attacking the carbon, around the carbon always four bonds are possible, right? So when this halogen is this nucleophile is attacking the carbon, automatically this bromine connected to the carbon will leave. Then this OH will make a bond with the carbon. So in SN2, the bromine is removing and the OH group is adding to the carbon. Both are taking place in a single step. Means first bromine is leaving, then OH is coming. No. Bromine is leaving, OH is coming. Both are taking place in a single step. That is called SN2 reaction. So when this OH minus group is attacking the carbon, we are getting a transition state in which carbon is connected to three hydrogen, one OH and one bromine. So this is a transition state, means they are not stable. They are not stable. Because here carbon is connected to five groups. Here a partial bond is forming between carbon and hydroxyl group, partial bond breaking between carbon and bromine. So after the intermediate, this carbon bromine bond will completely break and the carbon hydroxyl group bond will completely form. But see here, you see the structure of the compound. In the reactant bromomethane, bromine is connected to this side, right side. But in the product, OH group is connected to the left side. Why? Because the OH group is coming from the back side, so they are not able to attack through the front side, right? So that's why the product is having inversion of configuration. We can say they are having inversion of configuration. Okay, so in SN2, S means substitution, N means nucleophilic, 2 means bimolecular, because here the rate of the reaction is depends on both the concentration of the attacking nucleophile and the reactant. So that's why they are called, because two molecules are there involving in the rate determination step of the reaction. So they are SN2 reaction, that is bimolecular. So here the product is having inverted configuration. This is a single step process, that is the bromine is leaving and OH group is attacking in the same step. Okay. Now see, this is the configuration as I said before. Here the compound is having inverted configuration because the group is not able to attack through the front side. Okay, so the bulky groups here, see, methyl halides due to the presence of three small hydrogen react more rapidly in SN2 reaction. So here the bond breaking and bond formation takes place in single step. Suppose all these three hydrogen atoms are substituted by methyl group. So what will happen? This is a normal bromomethane. Suppose I am taking the compound CCH3, CH3, CH3, bromine. So here we can say when the OH minus is attacking the carbon, it becomes hindered by the presence of three bulky methyl group. Hydrogen is comparatively small atom. So this is a tertiary one. Why? The same thing, bromine is connected to carbon. That carbon is how we did in case of normal one. We discussed about the classification, right? So the halogen connected carbon is connected to three carbon. So this is a tertiary haloalkane. So in case of tertiary haloalkane, the SN2 reaction will be comparatively slower. Why? Because the attack of OH minus group will be hindered by the due to the repulsion from these three bulk groups. Means hydrogen, it's not a problem because hydrogen is a small group. So normally the tertiary alkyl halides are showing less reactivity in SN2 reaction, because if any bulky groups are there, the reaction become hindered due to the repulsion from these three bulky groups. So this is the see here two CS3 groups are there, here three CS3 groups are there. So here tertiary, this is tertiary one. So due to steric effect, this primary halide is more reactive in SN2 than secondary than tertiary. Okay, so this is the order of the reaction. Now one more mechanism is there, that is SN1. So before I said the SN2 SN1 mechanisms are there. SN2 means it is a single step process. SN1 means this is a two step process. In SN1 I am taking the compound, hydrogen is there, here CH3, here CH3. So here the halogen should be replaced by the means the nucleophile. So it is a two-step process, means in the first step the OH minus is there but it is not attacking. The first step, the halogen is leaving from the compound and corresponding intermediate is forming. That intermediate is called carbocation. Why they are called carbocation? Because the carbon, when the leaving group, when the halogen is leaving from the carbon is getting a positive charge. This species is called carbocation. Okay, so this is the carbocation. So in the second step, the OH minus group is coming to the role. That is the carbocation is attacked by the OH minus. This is the positive charged carbocation. OH minus is attacking the carbocation and they are forming CH3. Here hydrogen is still there and this will be OH group. So what is the difference between SN1 and SN2? This is substitution nucleophilic unimolecular. Here two-step process, right? Means in the first step halogen is removing. In the second step the OH minus is attacking. In the previous one the leaving and attacking takes place in single step. So in this reaction, the first step is the rate determining step. In this reaction, OH minus is not participating in the first step. So the rate of the reaction depends on the slowest step. That is the first step. So here the rate of the reaction depends only the concentration of the alkyl halide we are taking. So here this is a unimolecular reaction. Okay, so here we have two possibility. In the SN2 reaction, the product is having only one configuration, that is inversion. Whatever the configuration of the reactant, opposite will be for the product. But in SN1, we have two possibility. Because in the first step, we are getting a carbocation, right? Second one, the second step is the carbocation is attacked by the nucleophile. So there is possibility, two possibilities there means the OH minus can attack from the same side through which the halogen is removed, or the OH minus can attack from the back side of the compound. Okay, if the OH minus is coming from the same side, the configuration, that is the arrangement of atoms in the molecule, is similar to that of the reactant. See, from wherever the halogen is eliminated, the same position OH group is coming. This is called retention of configuration. Retention. Another one, the OH minus is attacking through the back side. There is a possibility. So the product will be like CH3 here, CH3 here, CH3 here. The OH is coming in the opposite side. This is inversion as we get in the previous one. Okay, in the previous SN2 we got the inverted product. The same way we will get inverted also. So there is a 50-50 possibility for both. Okay, so we are getting a racemic mixture of product in this reaction. SN1, that is a first step, one-step process. SN2, two-step process. The first step the group is removing. In the second step, the new group is adding. Okay, so here the rate of the reaction depends only on the first step, that is the slow step, because in the kinetics we studied in a multi-step process the rate of the reaction depends only the slowest step of the reaction. So here the slowest step is the first step, rate determining step. So the halogen is removed. So the rate of the reaction depends only the concentration of the halide, means alkyl halide. So this is a unimolecular reaction. So this is the overall mechanism. So if you coming to the mechanism, we are getting a carbocation intermediate here, right? So if the halide we are using is, if the alkyl halide is CH3X, the carbocation we are getting in the first step is methyl carbocation. If you are taking bromoethane, we are getting the carbocation, means halogen will be here. So this halogen is eliminating and we are getting a carbocation, and the carbocation will be like this. This is the halogen containing carbon is connected to one carbon. So this is methyl carbocation and this is a primary carbocation. Here the positively charged carbon is connected to one carbon. Secondary carbocation means we can say this is the positively charged carbon, means from here only the halogen is removed. This is a secondary carbocation, means the halogen, the positively charged carbon is connected to two carbon, secondary. Tertiary means the positively charged carbon is connected to 3-methyl group. This is tertiary. If you check the stability of the primary, secondary, tertiary carbocations, the tertiary carbocation is more stable than secondary, which is more stable than primary. Why? We know that Alkyl groups, all the alkyl groups, it may be CH3 group, whatever it may be, CH3 or CH2, CH3, all these groups have a plus psi effect. Plus psi effect means electron releasing effect. Means carbocation means they have a positive charge, means they are electron deficient species. Means they have no that much stability because of the deficiency of electron. So when the alkyl group is there, which is connected to the carbon containing positive charge, this alkyl group will give the electron density towards the positively charged carbon, and then the carbocation will get stabilized. So in the methyl carbocation, no CH3 groups are there. But in primary, only one CH3 group is there. So these CH3 group is due to the plus psi effect, they are giving electron density towards the carbon, and they are increasing the stability of this primary carbocation. If you come to the secondary, we have two methyl groups. They are again giving the electron density towards the carbon. Again, the electron density on the carbon is increasing. So the stability will be again higher than that of the primary one. If you come to the tertiary one, we have three alkyl groups. So what will happen? Three alkyl groups will give electron density towards the carbon. So electron density increasing means they are more stable because they are electron deficient carbon. So tertiary carbocations are more stable because of the presence of C. Here the methyl group is not compulsory. You can add any of the ethyl group. Suppose instead of CH3, here I am writing CH2, CH3. No problem. The same thing will be there. Okay, so these groups are giving the electron density towards the carbon, and they are increasing the electron density, so they become stabilized. So due to the stability of this intermediate forming in the first step of SN1, that is the stability of the carbocation, tertiary haloalkanes are more reactive in SN2 than secondary, which is than primary. Okay, that is the order. So in SN1, it is opposite to that of the SN2. In SN2, we know due to the steric repulsion, tertiary is not reacting that much faster. But in because that's a first one-step process. In SN1, due to the stability of the intermediate, that intermediate is not forming in SN1. Tertiary is more reactive than secondary, which is more reactive than primary. Okay. Next one, reactions of haloalkane. So next one, first one is optical activity. So optically active compounds rotate the plane of plane polarized light. This one I already discussed in the chapter coordination compound. What is polarized light and unpolarized light? Polarized light, unpolarized light means the light particles are vibrating in all directions. When this unpolarized light is passing through a polarizer, the light particle will start to vibrate in one direction. So that is called polarized light. So this is unpolarized light and this is polarized light. So when this polarized light is passing through an organic compound, this compound, if the compound is capable to rotate the plane of polarization of this plane polarized light, either into right direction or into left direction, the compound is called optically active compound. Getting it right? The polarized light is passing through a compound. If the compound is rotating the plane of the plane polarized light, the plane of the polarized light into left or right direction, the compound is called optically active. If the compound is not rotating the plane of polarized light, the compound is optically inactive. Okay, if the compound is rotating the plane of polarized light into right direction, this compound is optically active and is called dextrorotatory compound. The compound is rotating into left direction, that compound is optically active, but it is called levorotatory compounds. Okay, so then not only we can say the compound is optically active in nature. Now these dextrorotatory and levorotatory compounds are means there are the new compounds we are getting, right. So the asymmetric carbon, if in the organic compound have a carbon that is asymmetric carbon, or we can call it as chiral center. Chiral center means the carbon is connected to four different groups X, Y, Z, P. This carbon is called chiral group. Okay, so the chiral compound is always producing non-superimposable mirror image. So this one I already discussed in the coordination compound chapter. I'm taking my hand here. So I'm placing a mirror here. So I'm getting the mirror image. Now I'm not placing like this. I'm taking the mirror image and placing on the other one. This is the mirror is here. I'm placing my hand on this mirror and we are getting the image here. So this is same. Okay, I'm getting the correct image of this my left hand in here. So and I'm not placing like this. I'm taking this image and placing on the other one. Okay, so this is not superimposable, means these are not equal. See, this is superimposing, not superimposing. They are considering in wrong manner. So that is not superimposable mirror images. So chiral molecule will always produce a non-superimposable. See, this is an example for chiral C. If you take this C and placing on this one, this is not superimposable. But if you place A on A, that is superimposable. The non-superimposable mirror images are called chiral molecules and superimposable are achiral molecule. Okay. So chirality means the same thing. The mirror images cannot be superimposed by rotation. If you do the rotation also, we cannot get the superimposable images. Okay. That is called chiral center. Now enantiomers. Enantiomers means they are stereoisomers related to each other and the non-superimposable mirror images. The non-superimposable mirror images are called enantiomers. That we are getting. We are getting two images, means the non-superimposable images of the object we are getting here. That two are called enantiomers. Okay. Now, if you rotate the molecule, you are getting 50% of, means I am having, in the previous one I took one compound. This compound is rotating the plane of polarized light into right direction and left direction, right? Suppose I have 100 molecule. 50 of the 100 molecule is rotating the light into left direction. Remaining 50 is rotating the light into right direction. Okay, this is the polarized light, and when this polarized light is passing through this compound, half of the molecule is rotating the light into right direction, half into left direction. Now this compound we can call it as racemic mixture. Equal, 50-50. Okay. Okay, that's all. Now retention. Retention means, as I said before, the reactant and the product is having same configuration. I am starting from this one. CH3Cl. I'm getting the product CH3OH. So here see the position of chlorine and OH are same. That is retention product, retention configuration. Okay. See, this is, so we have inversion, racemization, retention. Inversion means the reactant is in opposite side. Retention means same side. Racemization means both are equal. Means 50-50 of this mixture is called racemization. Okay. Now the second type of reaction is elimination reaction. Elimination means from this haloalkane, I'm taking a haloalkane here, CH3, second carbon, hydrogen, halogen, hydrogen. From this compound, halogen is removing from here, hydrogen is removing from here. So this double bond is moving here in order to balance, because carbon around carbon there will be 4 bonds, right? So we are getting an alkene. So that compound is alkene. C, 2 hydrogen atoms are here, and here 2 hydrogen atoms. So elimination reaction means halogen from one carbon. The halogen connected carbon is called alpha carbon, and the adjacent carbon to this alpha carbon is called the beta carbon. So halogen is removing from the alpha carbon, hydrogen is removing from the beta carbon. That is called elimination reaction. As a result of the elimination reaction, the alkene molecule will, that is the unsaturated molecule will form. Okay, why this hydrogen is removing? This reaction takes place in presence of a base. Bases are H plus acceptors, right? So the base is taking H plus ion from the carbon. H plus means they are not taking the bonded electron. They are taking the hydrogen as H plus. So these bonded electrons are moving between the carbon. So an alkene is formed. Okay. Now, see another reaction. See, reaction with the metal. Before that, see, this is the reaction. Here, the elimination is taking place. So, in the elimination reaction, again, we have some difference. So, this is the reactant. Okay, so this is alpha carbon, halogen connected carbon. We have 2 beta carbon atoms here and here, right? So, what will happen? Here, the halogen is removing from this alpha carbon. Hydrogen is removing from either from here or from here. If the hydrogen is removing from this beta carbon, the double bond will form between these two carbon. That is the pent-1-ene product. Another possibility, halogen is removed from, because so halogen is only there, but the hydrogen is removed from this beta carbon. The double bond is formed between the second and third carbon. This is the product. So pent-1-ene and pent-2-ene are the products. So the major product is here the hydrogen is removing from the carbon containing again less number of hydrogen atom. So pent-2-ene is the major product. Hydrogen is removing from the carbon containing less number of hydrogen atoms. Getting my point, right? Okay. Now, reaction with metals. See, when the haloalkanes are reacting with a metal like magnesium, the magnesium metal will be inserted between the alkyl group and the halogen, and the compound produced is called Grignard reagent. So Grignard reagent, commonly we can call it as the formula RMgX. R is the alkyl group, X is the halogen. This is the inserted magnesium. This is called Grignard reagent. So that's how these are reacting with the metals. Okay. And these Grignard reagents are used in many reactions as starting materials also. Due to the carbon having more electron, the carbon magnesium bond in the Grignard reagent is highly polar but covalent in nature. We know that. Okay. So this is the C. Many reactions we can use the Grignard reagent like this. Okay. Now another one, Woods reaction. When the halogen alkene react with sodium, the hydrocarbon will form. That is two molecules we have to take. So the sodium will react with the halogen to produce sodium halide. So this is called Woods reaction. So Woods reaction means the halogen alkanes are converting into hydrocarbon. Okay. Next one, the reactions of haloarenes. So in the reactions of haloarenes, we can say many reactions are there, but we are considering the important reactions. So here, first one, nucleophilic substitution. Nucleophilic substitution means the same thing that we discussed in case of alkyl halide, but because here the ring is there, aromatic ring is there. Resonance effect. Resonance effect we discussed in the, you know that you studied in the grade 11, right? Because it is the jumping of electron through the aromatic ring. So this haloalkene is showing resonance effect. So the electron density is concentrating on para ortho and para positions, right? So there is a resonance structure. So due to this resonance, see here from the chloride is moving here. So these electrons are moving to next position like that. This is the movement of electron, jumping of electron. So due to the resonance process, nucleophilic substitution will take place in the compound. Okay. So difference in the hybridization of carbon and halogen. See here in this compound, the haloarenes means the halogen is always connected to sp2 carbon atom because the halogen is a part of aromatic ring, so they are connected to sp2 carbon. But in haloalkene, they are connected to sp3 carbon. That is the difference. So the bond length in CCl in haloalkene is 177, but in haloarene is 169. Why? Because in resonance, due to the resonance process in haloarene, the carbon halogen bond have a double bond character. See, here you can see due to the jumping of electron, there is a double bond character between carbon and halogen. So due to the double bond character, the bond becomes so closer, means bond length is less. That's why the carbon halogen bond in haloarene is 169 picometer. At the same time, other one is 177. Due to the resonance, the carbon halogen bond in haloarenes have a double bond character. Okay. Now, the instability of phenyl cation. Phenyl cation produced by the ionization are not stabilized by resonance because so NSN2 mechanism doesn't apply because it is different from that of the haloalkane. Now, due to repulsion, electron-rich nucleophiles do not approach electron-rich arenes. That is another one. Okay. Next one, replacement by hydroxyl group. If you are replacing this one, see, here the chlorine can be replaced by hydroxyl group. And next one, here we are replacing with the nitro group. So here ortho, meta and para positions are there. So whatever see here, we are getting ortho and para substituted product. See here, para only. Means depends on the group substituents, we will get different products in haloarenes. Okay, next one, electrophilic substitution. See here, I'm starting from this first one is halogenation. So I'm starting from chlorobenzene and reacting with chlorine in presence of FeCl2. We are getting ortho and para chlorobenzene. Okay, now here you see Again, we are reacting with HNO3, so the nitration is taking place at the ortho and para position. Okay, so electrophilic substitution is also due to the same reason, resonance process. Then sulfonation. Sulfonation means we are introducing SO3 group. Okay, another reaction is Friedel-Crafts reaction. Friedel-Crafts reaction are of two types, Friedel-Crafts alkylation and acylation. Alkylation means we are adding the alkyl group C. The reagent is always, in case of Friedel-Crafts reaction, that is anhydrous aluminum chloride. So here the alkyl halide is taking, so the alkyl group is substituting at the ortho and para position. We are getting mixture of the product. Okay, so acylation means acyl group will be introduced. Acylation means the acyl group, instead of the alkyl group, acyl group will be there. That is the difference. Okay, now the reaction with metal. So we discussed about Wood's reaction in case of normal haloalkane. So this is Wood-Fittig reaction. So here the haloalkane is there. So reaction with sodium, we are producing toluene. That is the alkyl group is introducing in this position. We are getting the compound. So Wood's Fittig reaction is a combination of Woods and Fittig reaction. What is Fittig reaction? Here the haloalkane on reaction with sodium, they are producing hydrocarbon biphenyl. Okay, the mechanism is not there, but you have to know the reaction properly. Okay.